So chapter 6, we're going to start talking about exponential growth. So, what is exponential growth? So this relates back to what we've been talking about, and it says if the growth rate is directly proportional to the amount present, we say that we have exponential growth. So for any positive real number, a and b, with b not equal to 1, the exponential growth function is f of x equals a times b to the x, where a is the starting value and b is the growth factor, or the growth multiplier, per unit x. So let's go ahead and take a look at example 1. So let's go ahead and make a table of values. Okay, so we have x and f of x, and let's use -3, -2, -1, 0, 1, 2, and 3. So if we calculate f of -3, that's 2 to the -3rd power. The negative exponents as we move it from the numerator to the denominator. So that's the same as 1 over 2 cubed, which is 1 over 8. If we do f of -2, we get 2 to the -2, which is 1 over 2 squared, which is going to be 1 over 4. F of -1 is just the reciprocal of 2. So it's going to be 1 over 2 to the first power, 1 over 2. The next one, f of 0, is my favorite, because anything except for 0 raised to the 0 power is 1. F of 1 is equal to 2 to the first, so that's going to be 2. F of 2 is going to be 2 squared, which is 4. And finally, f of 3 is equal to 2 cubed, which is equal to 8. So if we were to plot some of these points, we go to -3 and an 8, -2 and a quarter, -1 and a half, 0 and 1, 1 and 2, 2 and 4, and 3 and 8. And we get something that looks like this. All right. So one of the examples of exponential growth is called compound interest. But before we start talking about compound interest, let's see if we can figure out where it comes from. So let's start with simple interest. So if we think back, our simple interest formula is I equals P times R times T, where P was our starting amount, R is our interest rate, which we need as a decimal, not a percent, and T is going to be time. So we've used that formula in the past to calculate interest, but the account balance then would be P plus I, but I is PRT, so that's P plus PRT, or factoring out our P, 1 plus R times t. So the account balance at time t for simple interest is given by p times 1 plus r times t. So let's go ahead and do an experiment. So what is the account balance? So if I invest $100 at 10% interest, for 1 year, what's my account balance going to be? Well, P is going to equal to 100 times 1 plus my R, which is 0.1, times my T, which is 1. So that's 100 times 1.1, which is 110. As we would expect, if we had a 10% interest rate on $100 for 1 year, using simple interest, our account balance would be $110 after 1 year. Well, what if we compound the interest twice? So we're going to do the same thing. We have P equals 100. R is still going to equal 10%, but we're only going to go halfway through the year. So we're going to make T equals 1/2. So after 6 months, so when we do this the first time, we have 100 times 1 plus 0.1 times 1/2 is 0.5. It's going to give us 100 times 1.05, which is $105. So at this point, everything seems reasonable, because if I had a 10% interest rate for half of a year on $100, I would earn $5 of interest. So now let's compound once again. So we have 105 times 1 plus 0.1, and we have another half of a year. So then this is 105 times 1.05. And if we calculate that, we have 105 times 1.05. We hit enter, and we get 110.25. So when we calculated our interest this way, we ended up getting 25 more cents than what we had the first time. So the question is, well, where did that extra 25 cents come from? So we have these values. So where did the extra 0.25 come from? All right, so the difference between the first computation and the second computation is that when we compounded, right here at half of a year, we'll notice that we had a new value of P. Our new value of P was our previous balance from the first time. So that extra 25 cents that is present is actually the interest on the interest. So when you compound interest, they charge you interest on the interest that they've already charged you. That's what compounding interest does. So when we say we compound, we're going to have this type of effect. So turns out that most things that you want to buy in life, things like houses and cars, this is exactly how banks charge you interest. Nobody charges you simple interest. So it will be helpful for us to be able to calculate these things. So just as some interesting facts, how often is interest compounded on a mortgage for a house? They compound your interest every month. So you're paying interest on your mortgage balance every single month. If you've ever read all that fine print on a credit card, how often are they compounding your interest on a credit card? It varies, but for most of them, they actually do it daily. So every day they charge you interest, and then the next day they charge you on the interest they charged you yesterday, and so forth and so forth and so forth. So we'll do some computations to help illustrate exactly how this works. So the examples I gave make this sound all doom and gloom, but there's actually an upside to this, because most of you are still very, very young. Compound interest can be your best friend, because that means you have a lot of time on your side. So if you save money and get it invested in something that compounds your interest, you will be able to generate some very large balances over time. All right, so let's take a look at our next example involving compound interest. So a couple of observations and then we'll get to our formula. So something we may have noticed is if you look at this line right here, it simplifies to this, which is 105. So instead of having 105 for our new balance, we could have written it as 100 times 1.05, because this is 105, times what we were going to get again, 105 times this, times 1.05. Collecting, we would get 100 times 1.05 squared. So that was our starting amount. This was our number of times compounded. And this was our interest rate divided by the number of times compounded. So we would have to make some modifications, but if we kept doing this process and increasing the number of times things were compounded, our general formula starts to look something like this. So A0 is the starting amount. R is the interest rate. N is the number of times the interest is compounded per year, and T is time. So we can use this formula to calculate compound interest when we have a discrete number of times that it is being compounded. All right. So Yumiko deposits $10,000 in a 529 college savings plan that pays 4% interest compounded monthly. Find the function for the account balance and compare it with the simple interest model. Use the function to find the account balance after 4, 8, 12, and 20 years, and find the time it will take for the account balance to double. All right, so we want to use our model. A equals A naught times 1 plus R over N raised to the NT. So we identify our different parts. So our starting amount is going to be $10,000. Our interest rate is 4%, but we can never use a percent. We always have to convert to a decimal. So we get 0.04. The number of times it is compounded monthly. And there are 12 months in a year, so our N is going to be 12, and T is just going to be time. So this gives us A equals 10,000 times 1 plus 0.04 over 12 raised to the 12t. So that is our our compound interest formula. So for simple interest, we would have A is equal to the account balance plus the simple interest formula. So it's going to be P plus PRT, which we knew was P times 1 plus R times T. So we have 10,000 times 1 plus our interest rate, 0.04 times T. All right, so let's grab our graphing device and take a look at each of these. So we go 10,000 times 1 plus 0.04 over 12 raised to the 12x, and then we have 10,000 times 1 plus 0.04x. We press graph, and we don't see anything because our graph is on the interval -10 to 10 and -10 to 10, and we're starting at 10,000, so we're definitely going to need to adjust our window. So we'll make x 0, or x min 0. Let's make x max 30. We'll leave our x scale at 1. Let's make our y max 10,000, because that's where we start. We eventually want to know about doubling, so double 10,000 is 20,000, so we'll just do 30,000 to be safe. And then we'll go ahead and make our y scale in the thousands. If we press graph, we'll now get what our curve starts to look like. And we notice, as time goes on, the compound interest curve starts accelerating away from our simple interest model. They start out the same, but as we get interest on our interest, our growth rate continues to grow, right? So we get that curve that starts moving upwards away from our simple interest model. And we see that it starts growing exponentially as opposed to linearly. So let's go ahead and use our model to answer some of our questions. That's our compound, and this is our simple. All right, so we wanted to know, well, we found our function, so done. Use the function to find the account balance after 4, 8, 12, and 20 years. Well, since it's already in our calculator, that's easy to do. We just go back to our home screen, alpha trace, choose y1, we put in 4. Alpha trace y1, we put in 8, and alpha trace y1, we put in 12. And that gives us our first 3 values. And we put in the last 2 to see what's happening. Alpha trace, y1, and alpha trace for 20. I think I did an extra one, but that's okay. So based on the values that we got out of our calculator, we can at least guess a little bit about the last part as well. So we see after 20 years that the account balance is $22,225. So the last thing we were asked is find the time it takes for the account balance to double. Well, doubling is 20,000, so we see it's somewhere between years 16 and 20, and based on those outputs, we're going to guess it's probably closer to 16 than it is to 20. So for doubling, we want t when a equals 20,000. So we grab our graphing device, we go y equals, we don't need the simple interest formula anymore. So let's put 20,000 in, and when we press graph, we'll get our same compound interest curve, but then we're also going to see 20,000. So the value that we're looking for is actually at the intersection of those two curves. So we go second trace, and we choose our intersect, first curve, second curve, guess, and we get that our intersection occurs at 36 if we round. So about 17 1/3 years. Right here, right? All right, so let's talk about our next thing, which is Euler's number. So Euler's number is a special number in mathematics. Euler's number is given the symbol lowercase e. And like the number pi, it is an irrational number. So it turns out that e is a very interesting number. So let's see if we can figure out what the number e is. So to find e, we're going to take note of the following. E is the end behavior, or horizontal asymptote, of the compound interest formula as the number of times the interest is compounded goes to infinity. So in symbols, what that is we're going to have n going to infinity, and a equals a naught times 1 plus r over n raised to the nt. So first of all, what does that even mean? So if we're letting the number of times that the interest is compounded go to infinity, instead of something being compounded discretely, it means it's happening all of the time. So this is going to lead to the phenomenon of called continuous growth. So to simplify the calculation, let's let A naught equal R equal T all equal to 1. So that would leave us with A is equal to 1 plus 1 over n raised to the n. And we want to let n go to infinity. So let's put this into our calculator. And see what happens. So 1 plus 1 over n, but our calculator only knows x's, raised to the x. So let's do some computations. We want to let n get really, really big. So let's see what happens. So let's do n of 1,000. We get 2.71692. Let's do n of 100,000, or y of 100,000. We get 2.71826. Let's do 100 million. That's getting pretty big. So it's 100 and then 6 zeros. 1, 2, 3, 4, 5, 6. We get this value. And let's do 100 billion. So that's 100 and then 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we get this number. So let's go ahead and do this then. If you notice on the right-hand side of your calculator, the secondary function on the division key is actually the number e. So we notice after we get out to 100 billion, our calculator, when evaluating that, gives us exactly the same number as the number e. We'll also notice that each time we increase this, the first time they were the same to 2.17. The next time, these two numbers were all the way the same out to 2.7182. And then these were the same, 2.7181. And then finally, 1818. And then lastly, this guy goes all the way out, right? So the bigger n gets, the closer we get to that n behavior. So according to our graph, the n behavior, as we let the number of times the interest is compounded goes to infinity, that quantity right here, so 1 plus 1 over n raised to the n, goes to e as n goes to infinity. So as that number gets really, really big, as n gets really, really big, 1 over 1 plus n to the n goes to the number e. Well then this, if we let n go to infinity, of a equals a naught times 1 plus r over n raised to the nt, we get that this goes to a0 times e to rt. And we do that by making some substitutions and using that same formula. So oftentimes, for continuous growth and decay, we change the a to a p, because oftentimes when we're talking about continuous growth, we're no longer talking about account balances, we're talking about biological things. So we think of it as a population instead of an amount, but it doesn't really matter because you can call a variable pretty much anything you wish. All right. So now, let's go ahead and do example number 3. So radon 222 decays at a continuous rate of 17.3% per day. How much So how much will a 100 milligram sample of radon 222 decay to in 3 days? So let's use our formula. We have A is equal to A e to the RT. So a couple of things we need to take note of. When we have a decay rate, so when we grow, R is going to be bigger than 0. When we decay, R is going to be less than 0. So we have our decay rate. So when we put this into our formula, we have our starting amount, which is 100 milligrams. So we have 100. E, which is Euler's number, R, and we're decaying, so we put this as a percent, as a decimal, so 0.173, but we're decaying, so it's negative, so negative 0.173 times T. We're then told that we want to know how much is left after 3 days. So that's A of 3. So then we put that into our calculator, 100. And it's worth noting our calculator has a separate E button for when we want to put an exponent on it, because it happens so often. If you go down the left-hand side of your calculator this time, the secondary function on the button labeled ln, which is left of the number 4, has the E, and then it automatically puts you in the exponent, so negative 0.173 times 3. We hit enter, and we have 59.51, so we're going to go with 51.5 milligrams. So if we're decaying at a rate of 17.3% per day, we would have approximately 51.5 milligrams left. So notice this is different than linear, because if we are losing 17.3% per day and we times that by 3, that's 51.9. If we do 100 minus 51.9, we get an incorrect answer of 48.1. That would be an example of linear decay, which is the same as simple interest, right? Not the continuously compounded. So we need to be careful when we're working these types of problems to not fall back on our linear reasoning, because it will not work. All right, so to resolve this, we're going to need to use our continuously compounded interest formula. If it were simple interest, 10% of 1,000 is 100, so after 1 year it would be 1,100 if it were simple interest. But we have P equals P naught e to the RT, and our starting amount is going to be 1,000. Our interest rate is going to be 10%, but as a decimal, it's going to be 0.1. And our time, this time, is going to be 1 year. So 1 year, so T equals 1. So we get P is equal to 1,000 times E raised to the 0.1 times T. And then p of 1 is going to be 1,000 times e raised to the 0.1. And we get $1,105.17. So in this situation, we would have gotten $5 more using continuously compounded interest than if we would have used simple interest. Well, $5.17 to be precise. All right. Let's get ready to take a look at our next example. So, an exponential function can be determined from 2 points. So our general exponential function is f of x equals a times b to the x. It's worth noting if 1 point is the y-intercept, if the y-intercept is given, f of 0 is the y-intercept, would be a times b raised to the 0 power. But what's anything raised to the 0 power? 1. So that's a times 1, which is just a. So the y-intercept is 0, a. So if we're given the y-intercept, we can actually just plug it in directly for the a value and then determine what the base has to be. So find an exponential function that passes through the points -4, 2, and 2, 8. So we start with our f of x is equal to a times b to the x. Neither of those is the y-intercept, so we'll have to do this problem in its full generality. So we know when we put in -4, we're going to get out 2. So f of -4 is equal to a times b to the -4, and that is supposed to equal to 2. And we also have that f of 2 is equal to a times b squared, and that is supposed to equal to 8. So this gives a nonlinear system of equations. But we'll notice something. Both of them have an a in them, and they have exactly 1. So we can always divide one equation by the other to eliminate the a's. So if we take a times b squared equals 8, and we divide it by this equation on both sides, we would have a times b to the -4 is equal to this side divided by this side of this equation, which is 2. And what will always happen is the a's reduce out. B squared divided by b to the -4th. When we divide two things with the same base, we subtract their exponents. So 2 minus a -4 gives me b to the 6th is equal to 8 divided by 2 is 4. So then solving we take the sixth root of both sides, and we get b is equal to the sixth root of 4. So now that we know b, we can plug it back into either equation. It doesn't matter. So I'm going to pick the one on the right because of no reason whatsoever. So that's a times the sixth root of 4 squared equals 8. And so that simplifies to a times 4 squared is 16, so it's the sixth root of 16 is equal to 8. We divide by the sixth root of 16 and divide by the sixth root of 16, and we get a is equal to the sixth root of 16. A is 8 divided by the sixth root of 16. So we could try to simplify this. 16 breaks down into 4 and 4, 2 and 2, 2 and 2. So 16 is 2 to the 4th. So to simplify this further, to rationalize the denominator, we would need to multiply the top and the bottom by 2 squared, because then two things with the same base add, and that would give us 8 times the sixth root of 2 squared, which I'll just write as 4 now, over the sixth root of 2 to the sixth. But if we have the exponent and the root are the same, they reduce out. So that's the sixth root of 4 divided by 2. So finally, a is equal to 4 times the sixth root of 4. So now we know a and we know b. So that gives us f of x is equal to our a, 4 times the sixth root of 4 times b, which was, where did I write b down? Sixth root of 4. So oftentimes you're just going to want to approximate these, and in the homework they're going to have you round down to, I believe it's 3 decimal places. So the question you might be asking is, well, how the heck do I do a sixth root on my calculator? It's a good question. So let's open up our calculator. If we need to calculate the sixth root of something, so say the sixth root of 4, you press your 6, and then you go to your math key, which is in the left-hand side, and you go down to choice number 5, and notice it has the little X and then your radical symbol. You have to type the 6 in first and then press that button, and notice then it makes the sixth root of 4. So that's the sixth root of 4, and if I times that by 4, I would get 5.039. So rounding to 3 decimal places, I would get 5.040 times the sixth root of 4, which we have on the previous, rounding to 3 decimal places, we would get 1.260 for our decimal approximations. So a lot of that algebra can be avoided by just getting the decimal approximations, and as I mentioned in the homeworks, they're going to ask you to round, if I remember correctly, it's 3 decimal places is what they ask for. So that's what we did here, but if they ask for something different, obviously round to whatever they say, right? And that would be our exponential function that contained those 2 points. All right, well, let's take a look at our next example. So we want to find the equation of this exponential given this graph. Okay, so it's actually the same problem that we just did. So we identify our points. Well, we have 0, 1, and then we have another point over here, which is 4, 3, right? Turns out this one's a little bit easier because what were we given? What is the point 0, 1? That's our y-intercept. So then this is the point 0, a, so it implies that a is equal to 1. Well, if we know our model is y equals a times b to the x, and we know a is 1, then this is just b to the x. So now we can just solve for our unknown point. So we have 3 is equal to b to the 4th power. So we take the 4th root of both sides. So the 4th root of 3 is equal to b. So then y equals the 4th root of 3 raised to the x. So something that we may or may not remember is fractional exponents. So if I have x raised to the a divided by b, this is the same as the bth root of x raised to the a power, or the bth root of x raised to the a power on the outside. Well, if that's the case, using fractional exponents, and exponent laws, we have the following. If y is equal to the 4th root of 3 raised to the x, this is the same as 3 to the 1/4 raised to the x. And if we have a power raised to a power, what do we do with our exponents? We multiply. So this is the same as 3 raised to the x divided by 1. And we'll get some use out of that technique in some later sections. It's often helpful to rewrite things in this way. So that tells us then that it's going to triple for every 4 units of x, right? Because when x is 4, we're going to multiply by 3. When x is 8, we're going to multiply by 3 squared, which is we tripled again, and so forth. All right. So this one is going to be similar to the one we did before, because we weren't given the y-intercept. So we need to identify couple of points on this. So we have one right here at -2 and 2. We also have another point over here at 2 and 1. All right. So we set up our system of nonlinear equations to resolve this. So f of x is equal to a times b to the x. And we know that f of -2 is going to equal a times b to the -2, which is going to equal 2. And we know that f of +2 is going to equal a times b to the 1, which is going to equal to, 2, and it's going to equal 1. So we have our two equations right here. So if we divide a times b squared equals 1 by a times b to the -2 equals 2, and we divide both sides, Our a's reduce out, as always. B squared divided by negative b squared is b to the 4th power is equal to 1/2. So we take our 4th root of both sides, and that gives us b is the 4th root of 1 over 2, which is the 4th root of 1 is just 1 over the 4th root of 2. And now that we have our b value, we can plug back into either equation. So that gives us a times 1 over the 4th root of 2 squared is equal to 1. That gives us a times 1 over the 4th root of 4 equals 1. So we multiply both sides of our equation by the 4th root of 4, and we multiply by the 4th root of 4, and we get a is equal to the 4th root of 4. So then our equation is the 4th root of 4 times our b, which is 1 over the 4th root of 2 raised to the x. And that would be the equation of that exponential curve.